All right, so today we are going to start looking at covalent compounds. Um, Ionic compounds we've looked at in that their bonding is pretty simple. You have a positive thing and a negative thing that are attracted to each other, and they're able to kind of form a bond together. But today we're going to start looking at what happens when we take multiple nonmetals together, because we know that they're not going to make ions, they're not going to make charged things, but we're going to see that they can actually share their electrons together, and we're going to see how they're going to do that. But first, we're going to have to introduce something called the Lewis structure. And it's going to be the way that we're going to be describing both molecules. I mean, we could also describe individual atoms. Good morning. Individual atoms or ions with Lewis structures, and that would look something like this. If we were to take sodium, for example, what we do with the Lewis structure is we display the valence electrons that are going to be part of this atom. So if we kind of look back at where sodium is on our periodic table, it is in group 1A, of course. As a result, we're expecting it to have one valence electron. And we display that with a little dot. So this here is our valence electron. And that's going to be a part of all of our Lewis structures. And if we take a look at chlorine, chlorine has 7 valence electrons. We would draw that probably something like this. It does not matter which, side of the atom gets that one electron, but what you want to kind of keep in mind is that we will form pairs after the fourth electron. So just like, do you remember when we were filling those boxes out when we talked about electron configuration? You know how we kind of filled them out singly before we started pairing them off? The same thing would be here true as well. So if I were to really draw the chlorine step by step, we would put an electron here, then one here, then one here, then one here. So that's 4. We have 3 more to give. And then we would start pairing them off after that. And so we're going to see that that's going to be important later. Of course, it does not matter which one we pair off. We could have instead, left that one at the bottom lonely. That's okay. No problems. And so we're going to see that what happens in the chemical reaction between these two is that this valence electron will end up going to chlorine. The sodium will give up its electron to chlorine, forming the sodium plus ion. And then we'll have our chlorine with 8 valence electrons and a -1 charge. And then those would be attracted to each other, and we could describe their bonding this way. But it's kind of gratuitous, perhaps is the word. It's excessive. Most people are able to just say, okay, got it. They are charged oppositely and they can go together. Not a problem. So, but if you like to visualize things, go right ahead. If that helps you, by all means. That's how we would do it. Typically, we put these in brackets if they're charged. And that's going to be something we're going to do throughout this course. If you end up taking 111 in the fall, you're going to learn how to more accurately deal with charge in Lewis structures. We're going to kind of teach you in this class we kind of teach you half of the Lewis structure, and then you do like kind of the finishing touches in 111. So we're kind of just working right now with like kind of skeleton structures, and that's going to be enough for our purposes in this class. And then if you take 111, you'll learn more realistic structures that are a bit more complicated. But let's keep it simple. So with a covalent compound, we're going to see that valence electrons are shared between atoms. If we look back at that ionic one we just did, there was no sharing. Sodium gave its electron away, chlorine took it. That's the end. Complete taking away of the electron. However, with covalent compounds, we're going to see they're going to share them. And we even have the word covalent. Co meaning together, right? And then valent will refer to the valence electrons. So the word itself describes how they're sharing. And how covalent compounds look something like this. If we have our good friend methane, let's take a look at that. I'm just going to show you the structure of methane. And we're going to learn in a little bit how to come up with these structures ourselves. All right, so you might see a structure that looks something like this. And this would be a shared pair of electrons. Electrons have to be shared as pairs. They can never be shared. You can't share one electron between two atoms. It always is a pair. And if, this is kind of one way to draw it, but typically we'll actually see them drawn like this instead, with lines to represent the two dots, just because the lines are a bit neater. If we have a lot of dots going on, it's a little bit easier to see which ones are bonding and which ones are not bonding. Right now, all of these electrons are bonding, so we don't have to worry, but these are the same thing. So that line there connecting the two atoms is the same thing as one shared electron pair. Sometimes what happens is you'll end up sharing multiple pairs of electrons, which is okay. Just another one here. We would perhaps redraw this a bit more neatly. Where here now we're sharing... Ooh, that's a terrible arrow. This would be two shared pairs of electrons. And that would be 4 electrons total then. 2 pairs, right? So 2 pairs means 4. You'll see that sometimes we'll also end up with unshared electrons, which are called lone pairs. And we're going to see that lone pairs are going to be pretty important when we start talking about the properties of a lot of these compounds. So we can share multiple pairs of electrons. Got to share at least one pair, that is. You can't share just one electron. And so we can see we can also share multiple pairs. And we would call that a double bond. And sometimes you have triple bonds as well. So let's go ahead and learn how to tackle some of these. So there's a process for this. It's going to be just kind of a step-by-step thing that we're going to teach you here. There's other ways to do it. We'll learn a few more next semester if you do that, but we're going to kind of just stick with one way right now. So, and it's going to be a procedure that you can just kind of follow every time. It'll get you where you need to go. What you want to do first is you want to count up all the valence electrons. And so we're going to see that we have in this compound we have carbon plus 4 hydrogens, That's what that formula tells us. Carbon has 4 valence electrons. It's in group 4. And then hydrogen has 1 valence electron each. That gives us a total of 8 valence electrons. All right, so again, we use the periodic table to tell us the valence electrons just in case we've forgotten. Let me draw it out here. And we're not going to really be messing with most of the things in, definitely not the D block, but remember our valence electrons follow this pattern. So everything in these columns has that many number of valence electrons. So carbon being over here has 4 valence electrons. Hydrogen up there has 1 valence electron. So overall we have 8 when we put them all together. All right. Cool. So second step now is we want to assemble our skeleton. And what this means is we have a single bond or one shared pair between the central atom and each outer atom. Generally speaking, usually the first atom in the formula is the central atom. Usually. Just a couple of notes. Hydrogen and fluorine can never be central atom. We're going to see why in a little bit. But hydrogen and fluorine can never be in the center of your structure. Okay, but let's go back to our methane example. So CH4 tells us that carbon's in the middle. Usually your first atom written in the formula is the one in the middle. So we're going to arrange these hydrogens around the carbon. Typically you just do them 90 degrees apart just to make it as clear as possible. We're going to see this doesn't actually reflect the shape of the molecule, but that's something for a few days from now. So what we're going to do is we're going to want to form one single bond between the central atom and each outer atom. So we're going to do that by putting in a pair of electrons in between them. So from the central atom to every single outside atom. Notice we had 8 electrons to start. By making this single bond, we have used up 2 electrons. We have 6 left. So if we're going to keep making our single bonds here, we're going to keep using 2 electrons at a time. Hopefully it's okay if I just do these last 4 all together. We should use up all of our electrons. All right, and so we're going to actually be done with this structure. But technically what we want to do in our third step is ensure all atoms are satisfied. That means for most atoms, they want 8 electrons around themselves. Most things will want 8 electrons. The reason for that is that's going to be your noble gas configuration, right? That's the whole point of doing this. Chlorine took 1 electron so it could be like a noble gas. We're going to see the same thing is going to be here, true here as well. So we're going to see most atoms will want 8 electrons around themselves. There's a few that have exceptions, which we'll note here in green. For hydrogen, it wants 2 electrons. For beryllium, it wants 4 electrons. And for boron, that one wants 6 electrons. After that, everything else wants 8. So we don't have to worry about anything else. These are the only exceptions. And you'll notice these are kind of the first couple of atoms anyway. Beryllium is element number 4, boron is element number 5. Those are the only kind of exceptions. So these elements are happy with that number of electrons. Most atoms, though, want 8. So let's go ahead and look back at our structure of methane here. And we can see, remember these are shared pairs, which means that both atoms will kind of enjoy them. If we look at this hydrogen on the right, it has 2 electrons connected to it. Hydrogen only wants 2 electrons, so that hydrogen is happy. If we look at the hydrogen on the bottom, it has 2 electrons. And so do these other 2. They're all happy. And if we look at that carbon in the middle, well, it has 2, I guess I shouldn't draw, but 2, 4, 6, 8 electrons. Our carbon is also happy. All right, so that's kind of the purpose of doing all this stuff, is we want to make sure that all of our atoms will get to where they want to be. And most of them, again, want 8 electrons. And so we're going to see that there are a few things that we can do in step 3 if atoms are not satisfied. So if atoms are not satisfied, we have to tinker with our structure. And that can mean, for example, making multiple bonds. Or moving electrons around. But we'll look at that in a little bit. So let's do a couple of easier examples first. And then we'll... Oh, you know what? I forgot to... Oh no, I forgot to put a step in here that was not applicable for this particular one. So let's go ahead and actually call this one step 4. And we'll write step 3 just right above it. Oops. Give extra electrons to outer atoms as lone pairs. So in this case, we did not have any extra electrons. We used up all of our electrons just doing the skeleton. And so we didn't have any extra ones, so I kind of skipped that step. But if we had more electrons, we would start putting them on the outside atoms. And we'll take a look at what that's going to be in our next example here. And then after that, we're going to make sure that everyone is happy. So let's take a look at carbon tetrachloride instead. Let's do this one. So let's go ahead and work through all the steps. We're going to do this kind of step by step for a number of examples today, because again, practice is going to be our best way to do this. So your total valence electrons is the first thing we want to do. So that's going to be 4 from carbon plus 7 for each chlorine. So that'll be 4 times 7 because we have 4 chlorines there. That'll be 32 electrons once we add it all up. Just so we see that each has 7 valence electrons. And then we have 4 chlorines. And then, of course, this was carbon over here. All right, so we've got 32 electrons. Let's go ahead and assemble our skeleton. So I'm just labeling these steps because I just want it to be easy to follow what we're doing. You do not have to label all of your steps. That is totally up to you. All right, so we're going to want to assemble our skeleton by putting our central atom in the middle and putting a single bond to all of our outer atoms. So we had 32 electrons. We've used up 8 in our skeleton here. So we have 24 electrons left. What we want to do now, I'll do this step in, I don't know, light blue, I guess. We give pairs, starting with the outer atoms. And we usually want to give until they have 8 electrons around them. Obviously, we're not going to want to give them 10 electrons or something. We want to make them all happy. And happy is going to be 8 electrons, or if it's like a hydrogen or something, we would stop at 2. But for most atoms, again, it's going to be 8. So if we start giving some electrons to the chlorines, we want that chlorine to have 8, so we'll give it 6 more electrons. We have 18 left. Keep going. Next chlorine. Does not matter which ones you give these to. We'll see that that's going to be a phenomenon we'll experience a little bit later. We have 12 electrons left. There's another 6. And we have 6 left, so let's go ahead and give them up here to this last chlorine. And that'll be that. So we have used now all of our electrons. If we still had electrons, we would start giving them to the central atom, but that's not necessary here. Already that carbon is happy to begin with, so we don't even have to worry about it. All right. Step 4 is kind of evaluate and adjust. Let's just go ahead and check. Do all of our atoms have their 8 electrons? Looks like this chlorine has 2, 4, 6, 8. It's happy. So is this one, this one, this one. And then our carbon is also happy. All of our atoms are happy, so we are technically done. But oftentimes we would like to just redraw this so it's a little bit neater. We would redraw it with the bonding electrons as lines. And we would keep our lone pairs on our outer atoms. So we still have to draw our lone pairs if we're going to redraw the structure. Again, we're going to see those lone pairs are going to be important later on. Alrighty, so let's just take a look at this structure for a second, and let's evaluate it. Let's see some things that we can just come up with about this structure. We can see that the number of bonds here is going to be 4 bonds. Those are those lines in between them. If we look at how many bonding electrons we have, we know we have 4 bonds. Each bond is 2 electrons. So therefore we have 8 electrons that are in bonds. If we have non-bonding electrons, those are lone pairs. Let's see, how many lone pairs do we have? If we're asking for non-bonding electrons, we have to count every single electron. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have 24 non-bonding electrons, or 12 lone pairs. All right, so we can look at these things. Of course, we should see that our bonding and non-bonding electrons should add up to our total, which was 32. So we are good. All right, so just a couple of things we can kind of point out about a Lewis structure. So, these are kind of things I could ask you on an exam, for example, is how many, non-bonding electrons are in this molecule. And you would have to draw the structure and then come up with the number afterwards. Let's do it again. Here's one of our favorite molecules. Aha. All right, so we have 6 valence electrons from oxygen, and we have 2 hydrogens with 1 each. That'll give us 8 electrons total. This is from oxygen and hydrogen, of course. Remember, hydrogen is never something that could be in the middle. So we're going to put oxygen in the middle. And we're going to put a hydrogen on, each side. Or we could put them as 90 degrees. Doesn't really matter. And let's put a pair of electrons in between each one. So we'll use up 4 electrons. We have 4 left. All right, so next step, we would give these to the outer atoms. However, our outer atoms are already happy. Those hydrogens only want 2 electrons. They already have 2 electrons. So what we're going to do is give those electrons to the oxygen. So I'm just going to note that the hydrogens are already happy. So we give the extra electrons to the central atom. All right, and those are going to be over there. Let's evaluate our structure. Each of these hydrogens has 2 electrons, so those are happy. Our oxygen in the middle has 8 electrons, so it's happy. So we're good. We might redraw this. Like so. You could also, if you really wanted, you could totally draw it this way. That's okay with me. Does not matter. There's really no bearing. Or if you really wanted, you could draw it like this. I don't know, something like this. Who cares? I guess that one on the bottom is a little bit strange, but generally most people will draw them one of these 2 ways. Those are kind of the most common way to draw a Lewis structure. You're welcome to draw whichever way you like here. I would try and avoid that one on the bottom because it's just a bit strange, but I would technically be able to grade it still, so it would be okay. But instead of giving you bad ideas, let's just erase that. It never happened. So we don't have to think about that anymore. Alrighty. Any questions so far on any of these? Oh, she's scratching herself. Okay, in that case, let's go ahead and now look at a more complicated case where we're actually going to have to worry about rule number 4 there. So carbon dioxide. Our total valence electrons is going to be 4 from carbon plus 6 from each oxygen. That'll be 16. 12 plus 4, 16. Alrighty, so let's go ahead and put our skeleton together. Alrighty, so we'll have used 4 electrons. We'll have 12 left. Let's go ahead and give these electrons out. So we'll start giving them to the outer atoms. We'll use up 6. We have 6 left. We'll go ahead and give it to the other outside atom. We'll use up all our electrons. Let's evaluate. Our oxygens have 8 electrons. They are happy. Oh no! Our carbon there in the middle only has... He's only got 4 electrons. Oh no. What are we going to do? Well, this is where we're going to have to start sharing more things. So if you were to just try and move electrons around, I mean, we could do that. If we were to just say, okay, now we're going to move those 2 there, now we've made 2 atoms unhappy. So that's not going to be something that we're going to do. But when this situation arises, this is when we're going to start making multiple bonds. So when the central atom has too few electrons, we make double or triple bonds. Yeah, you can draw them in whatever way you like. So, if we are going to try and make this carbon dioxide happy, what we can do is, okay, let's try actually sharing this lone pair over here. Let's see what that would look like. I'm gonna just redraw that down here. I'm going to just redraw those 2 electrons in light blue so we can see. So now, remember that this means that it's sharing 4 electrons. So those 4 electrons are going to be part of both atoms. They're part of the oxygen, they're part of the carbon. So this oxygen still has 8 electrons. It's got 2, 4, 6, 8. So both of those pairs in the middle are shared by that oxygen. So it is still happy. All right, I'm just going to erase those numbers. This oxygen, 2, 4, 6, 8, still happy. And if we look at our carbon, we have 2, 4, 6. Uh-oh. Still not quite there. So, we have the option now to share another pair. To try and make this carbon happy. And so we have 2 options here. Let me use different colors so we can see. We can maybe dump that lone pair into making it shared, or we can take one from the other side. Let's see what these 2 would look like. All right, let's take a look here. So we'll keep our single bonds here. We have our shared blue bond and our shared purple bond. So now that is 6 shared electrons there. So this oxygen has 2, 4, 6, 8. It's happy. This oxygen has 2, 4, 6, 8. It's happy. Oops. And this carbon has 2, 4, 6, 8. It's finally happy. So this would work. We would have made all of our things happy. Let's take a look at what happens if we move that orange one instead, though. Excuse me. All right. Okay, let's go back to all of these crazy colors. Oops. So remember, these are... both of these are 4 shared electrons. So we're going to see this oxygen 2, 4, 6, 8. It's happy. Oh my gosh, go away. 2, 4, 6, 8 for that oxygen. It's happy. And now carbon in the middle. It's happy too. It has also a high little one. If we redraw these with the lines, we would end up with these two kind of options here. This is what it would look like if we were to redraw these. So we have these kind of two options here. And technically both of these are valid structures, but we had two options. Both of these work. This is not necessarily an isomer. An isomer, we'll see, is going to be something a little bit different. These are what are called resonance structures. So there are multiple correct ways of drawing the same structure. An isomer is going to be something where we rearrange the order of the atoms. In here, our order of the atoms is the same. These are just going to be resonance structures of each other. So these would be just like kind of multiple correct Lewis structures. That's what resonance is. So we had the option to either make a triple bond and a single bond, or 2 double bonds. Or what you could have done is made your triple bond to the oxygen on the right. That would totally work as well. We didn't necessarily draw that in this particular exercise, but these three are all resonance structures of each other. So they're all correct. And would kind of satisfy our atoms. They'll make them all happy. So all of these would be correct. However, we're going to see sometimes one of them is better than the others. Well, this would not be something that you would be able to know right off the top of your head, but 2 double bonds is going to be better than a triple and a single. So, in fact, this one is going to end up winning here, being probably the most likely to be the correct structure, just because 2 double bonds is going to be just energetically better. You would not be expected to know that, except now that I've told you, now you need to know it. But we're going to see that that'll be the case. We'll see in another example more resonance structures where, in fact, all of them will be equal to each other, where there's not going to be one that's better than the others. All right. Just so, let's see, let me clarify what an isomer can be. Okay, so an isomer could be something like, we can do, how about, yeah. these two, this one is called cyanate, and this one is isocyanate. We're going to see that these are going to be similar. How this one looks is like this, and the isocyanate, let's see, will look like this. These would be isomers of, actually no, these would technically be no, these are isomers. Yeah. So we can see here that the order is going to be different in between these. So here we have the oxygen connected to the carbon and the carbon in the middle. In the other one, we have the nitrogen in the middle. And so these would be isomers of each other. These would have a different arrangement of atoms. Whereas something like if we were to draw a resonance structure of the cyanate, here I'll redraw the cyanate here. If we were to draw a resonance structure of it, that might be something like this. This would be a resonance form here. Where here we have the same order of atoms, the same arrangement, but we've just kind of shifted some bonds around. So we basically, what's happening in the resonance is we're bumping a lone pair, turning it into a bonding pair, and taking a different bonding pair and turning it into a lone pair. So we're kind of just like pushing electrons around. So we're just shifting our bonds. That's what resonance is. Isomers are going to be completely different arrangements. So that's going to be the difference there. Okay? Exciting stuff. I'm glad you asked that. It's a good distinction that needs to be made. So it's a little bit earlier than I would normally introduce that, but that's okay. I'm very happy to answer questions, to pique your curiosity. So let's go ahead and look at now, let's look at the structure of carbonate. Let's take a look at this one. Notice this is going to be our first example of drawing a Lewis structure of something that is charged. So if we're to count the total valence electrons, we have 4 from carbon. We have 3 oxygens, each giving 6. And we also have 2 extra electrons. So this one is from the carbon. This is the oxygen. And this is the 2- charge. A 2- charge, remember, means you have 2 extra electrons. So we're going to want to take account of those in our total electron count. If we had a positive charge, we would see that we would take away electrons from our total. If we have a negative charge, we were going to add electrons to our total. So let me just write that down. If something is positive, you would subtract. And of course, you would use the number of electrons to make it work. So this is a 2- charge, so we need 2 electrons. If it was a 2+ charge, we would take away 2 electrons. So you would adjust the amount of electrons to make your charge. All right, so the total here is going to be, let's see, 24, I think. Let's see if I can do the math. 4 plus 18, 22 plus 2, yeah. So 24 electrons. Alrighty. Cool. Let's go ahead and do our skeleton. All right. So we have used up 6 electrons. We have 18 left. Alrighty, so let's go ahead and I'm just going to give 6 to each one. Hopefully that math is not too bad. We have 3 outer atoms, 18 electrons. Each one should get 6. Checking all of our things. We'll see the oxygens are all happy. And carbon is in fact quite sad. Poor, sad carbon. Only 6 electrons. So, again, we have options here. We could take a lone pair from that oxygen, or we could take a lone pair from that oxygen, or we could take one from this oxygen. If we do that, whichever one we end up choosing, we'll get a slightly different structure. Or here, let me use the colors here. The purple one would end up giving us this structure. I'm just going to go ahead and make it neat, if that's okay with everybody. Just so we can see very clearly what's happening here. If we went the blue route, oops. We would end up with this, and if we went the orange route, we would end up with our double bond on the right side instead. Okay, hooray. So, we have here 3 resonance forms. Right, it just kind of, the only difference, as you can see here, is where we've put that double bond. So in order to make that carbon happy, we needed to give it 2 more electrons through a double bond. And so we had the option of taking it from any of those potential oxygens. And we can see that these structures are actually all identical to each other. If we were to just rotate the molecules around, you know, if we just like rotate that the left one 90 degrees counterclockwise, we get the middle structure. Or if we did it another 90 degrees, we'd get the one on the right. They're all going to be equivalent to each other. And so, in reality, we don't just see one of these, we see all of them at once. And that would be drawn something like this. Where we would draw that indicating that we have kind of a hybrid structure. You know, I'm terrible at drawing this particular thing. Let's go ahead and let me find a better image of it. Let's take a look here. Okay, so here, actually, let me fix this real quick. Let me make a new tab so we don't have to worry about looking at myself over and over. Okay. Okay, so if we go ahead and let's look at Chrome again. Let's go to Wikipedia. Okay, if we go to carbonate, we're going to see here those kind of dashes to indicate that hybrid in between them. Or what that would look like in our Lewis structure would be something like this. Let's zoom in a little bit here. I guess they're kind of blurry, but this is what we're kind of going for here. So where we have a single bond for sure, and then that double bond is kind of shared between all of them. You don't have to worry about these charges here. That's something we'll come up with in 111. But we can see that bond is going to be pretty much equally shared between them. So we have 3 different resonance structures here. All of them are equivalent to each other. They're just, as you can see, rotated. And so as a result, our overall structure is a hybrid of them. And so experimentally, they find that the bond lengths for all of these are all the same anyway. So in fact, there's not one in particular that gets the double bond. It's just going to be equally shared between them as the electrons just kind of bounce around. Okay. So if I were to ask you for the structure of it, it says 2/3 on the card. So because overall it's a -2 charge, I don't want to teach you formal charge. That's something we cover in 111. But suffice it to say, in this particular Lewis structure, these oxygens each have a charge of -1 for reasons that you don't need to know. However, if we are to kind of split that double bond up between all of them, some of that negative charge is going to go onto the other oxygen in a process called delocalization. And that means that those negative charges are going to kind of be split among all the 3 oxygens. So we have 2 negative charges on 3 oxygens. So instead of these ones being -1 each, we would end up with 3 of them, all of which being -2/3 overall. Again, beyond the scope of this class, don't worry about it. This is not something we have to worry about here. So, but that's what would happen. We would distribute the charge along as well as distributing that double bond. So in the meantime, I'm going to just delete this so that nobody gets confused. All right, and so if we were to draw our structure, we would put it in brackets with the charge just to indicate the whole thing. So for us, we just put the brackets and put the total charge. And so we don't have to worry about figuring out where those charges are. But that's something we deal with next semester. Well, dude, get off that couch. He's oh my god, don't jump off the side. Hold on. Little one, come here, come here. Go down there. Go on, buddy. There you go. Okay, I thought he was gonna jump off the side of the couch. So, and he's like 6 pounds, so that would not be a good idea. What was I saying, by the way? Yeah, for us, we just put the whole charge on the side. We're done. You can, if you were to answer this, you could draw any of the resonance structures. If you wanted to draw your double bond on the right, you're fine. Go ahead. I'm happy to accept any of these as an answer. So if you were to submit this one, or this one, or this one, they're all correct. You may submit the one that you like. You don't have to do the hybrid one. So but understand that that's what happens in reality, is it's a mixture of all the resonance forms. Woo, exciting. Any questions so far? Actually, this is probably actually a good place to stop. Just because we would just do more examples. You do have your nomenclature homework. I am going to probably put this homework up as well if you want to start working on it, but it's not going to be due until next week. So, yeah. But you'll see that they don't take long, Eddie, the naming stuff. And you'll see that it gets a lot easier the more you do. So, don't worry. They're fast. And again, by the time you do it, unless you're cheating, perhaps, you will be a master of coming up with the names and formulas. And again, that's going to be such an important skill to have. That's why we do that. So, yep, exciting stuff. So cool. So I'll go ahead and here I'll do it right now so I don't forget. Let me put up your thing. I'll keep grading slowly as always. Though the new dogs are taking some time. I'm gonna go ahead and publish your Lewis structure homework so you guys can see it. That's a good question. I have no idea. Let's check your syllabus. Let's have a look. Oh, it's supposed to be next week, huh? Let's push the exam a little bit. Will we finish Lewis structures in time? I will think about this. So, presumably your exam should be Monday. It's really going to depend how much we cover by tomorrow. I don't think we're going to finish it. So, probably what we'll do is we'll make your exam a different day next week. So maybe we'll have it. I'll do a poll. I'll see what works for the most amount of people, and then we'll just do it then. What we might end up doing is we might just push it to the 8th, and then we'll push our exam 3 till after spring break, so you can spend your vacation studying frantically if you like. Or we'll figure something else out. So I'm happy to entertain suggestions. For now, I don't want it to be on. Of course, yeah, we'll definitely do a review. But I don't. We're not going to have it on the 1st. We're not going to be ready for it. So we'll come up with some options and we'll discuss them. So I'll put some options in Discord. We'll discuss them. We'll see what works for people, and we'll make it work. So, good question. I hate exams. I'm sure you guys do too, but as you know, they're important. So, anyways, the Lewis structure homework I am going to put up so you guys can start working on it if you like. You can start putting your stuff. You're not going to be able to answer everything right away. And so, but it is there if you want to start applying your skills right away. For that one, you will need a separate sheet of paper because it does not give you a lot of room. Or it's going to be asking you to draw the structure, so you may want to use like the back side of it or just get an extra paper. So, alrighty. If there's nothing else, I'll see you guys tomorrow. And I'll throw up our options in Discord. We'll play around and we'll see what to do with that exam. So, alrighty. Take care, everyone.